G'day, welcome back to another episode of Extractions&Ire. Welcome back to my home shed laboratory. And today's material science project is to make GLS glass, which is a gallium lanthanum sulfide glass. I don't know if it's going to work, as per always with all these Extraction&Ire videos. I haven't started this yet. I'm not entirely certain I know all the steps to get there, but, thanks for coming with me on this journey. Very quickly, I'm just going to talk about what GLS glass is and why anyone would care, and also what these elements are, because I'm sure lots of you have heard of them, but you probably haven't thought about them very much. And also how we, in this home shed, are going to be making some GLS glass a little bit later on. Well, hopefully successfully making. I can only assume positivity here. Let's talk gallium. Now, many people have probably seen or maybe even had the privilege of holding gallium. Now, gallium is a fantastic sample because it melts just above room temperature, so you get to sort of hold it and simulate what it was like when our grandparents got to play with mercury metal. In terms of chemistry, it doesn't come up in chemistry very often. It comes up in physics quite a lot. It's used in transistors and LEDs and that sort of thing. The ugly blue LEDs are gallium nitride. Gallium is used in a lot of semiconductor materials, so it doesn't get a huge amount of use in terms of tonnage, but a very wide use. So it's a very essential component of components. That's gallium. Lanthanum is perhaps the more interesting of these two elements, and by that I mean it is not interesting in the slightest. A couple of years ago, I did an entire ranking of all the 92 naturally occurring elements, and I ranked them from good to bad just based on, vibes and facts and that kind of thing. And lanthanum came in at 91 out of 92, just ahead of actinium, which I think is pretty unfair to actinium. I think lanthanum probably could have come last. Out of all the naturally occurring elements, I think lanthanum is probably the most boring. Like all elements, lanthanum does have some niche, obscure uses, but you might be asking, does it have any value? And the answer is absolutely not. And the reason that is because it's a rare earth. When you have a rare earth mine, you end up mining all the rare earths because they're all so chemically similar and they all end up in the same deposit. And so you mine all the rare earths and then you have to spend a lot of energy separating out all the rare earths. So lanthanum, as well as being the most non-useful of all the rare earths, is actually the second most common rare earth. There's always more supply of lanthanum than there is demand. It's basically a waste product from these rare earth mines. I can only assume they're putting heaps of this lanthanum just back in the ground. When you think about it, right? Think of all the neodymium magnets in the world, right? The things that power hard drives, electric cars, wind turbines, all the little fridge magnets you can buy for hardly any money. Those, by mass, are 25% the element neodymium. And for all the neodymium that was mined, there was an equal, if not a larger amount of lanthanum that was mined. And that lanthanum is used like nowhere. And we're going to keep needing more rare earths, so we're going to keep mining more lanthanum and just not using it. So which does give a bit of context for how we're getting lanthanum for this project, because I actually got it just in my local hardware store. They sell a solution of lanthanum sulfate or lanthanum chloride or something like that to remove phosphate from swimming pools. Once it hits phosphate, it gets solid and then drops out of solution, so algae and that kind of thing can't use the phosphate to grow. And this is actually, I think this is a similar procedure in what's used medically as well, because lanthanum is non-toxic. If a person has too much phosphate or something, I think it's a liver condition or something like that, then it can take phosphate out of their body as well. So each element is not completely useless. And this is an Extraction&Ire video, so someone will turn up in the comments who has done their entire PhD on lanthanum. I'm looking forward to reading your comment, but yeah, definitely not a super exciting element. But today we get to use lanthanum and gallium to make GLS glass. GLS glass is kind of an obscure curiosity, but it does have two distinct advantages over similar glasses. First of all, it is relatively non-toxic. Now, once again, when someone says relatively non-toxic, they mean that in the usual circumstance, they're using mercury, cadmium, lead, or arsenic. And in this case, what GLS glass is generally used for is infrared transmission. And generally, when you're talking infrared transmitting glass, was arsenic-based glass, which is where the toxic comes from. Gallium and lanthanum are not that healthy, but they're not that toxic. So compared to arsenic, they are very relatively non-toxic. The second is that high infrared transmissions. And this is key for a couple of components. It's not as far into the infrared. People often think about infrared transmitting glasses as for thermal vision or, thermal camera stuff. It's not that far. That's sort of the 8 to 10 micron range. This is more in the sort of early infrared. No one calls it the early infrared, but you know what I mean, 2 to 5 microns. When you think of glass, everyone thinks of, window panes and artistic sculptures, but another thing that, glass is used for in the modern world is the internet, right? The the internet runs over optical fibers, and those fibers are just made from silica glass. And it's crazy how the internet works. I mean, it's you kind of get the sense that, oh yes, I talk to a server and, I send my signal and then I get it back. And that kind of makes sense. But then you realize that your entire country's data is going over the same optical fiber line at the same time, which turns it into one of the most magical inventions of the 21st century. Like, it's crazy. We've taken normal glass and we can put so much information through one tiny fiber. It's just ridiculous. Because of, how good the internet is and how profitable it is, research has basically pushed silica glass to its absolute limit in terms of its transmission properties. Like, we cannot get better fibers in silica than we do now. It's crazy that we've managed to perfect glass making to this level. And when I say we, I mean, professionals. However, there is obviously going to be a fundamental limit with silica. And one of those fundamental limits is that it absorbs actually very strongly above 2.5 microns. So you can never use that silica glass, commercial grade silica glass that we use now for anything over 2.5 microns. And so if you wanted to do that, I don't know why you would want to do that, but we might need to in the future. There might be some quantum internet shit that we've got to do at 3 microns or something like that. And for that, we would need a whole new range of fibers. And there's a lot of competing sort of different glasses, fluoride glasses, but also these sulfide glasses. And if you had a 3 micron internet for whatever reason, then you could run it over this GLS glass. So that's kind of why this glass might be important. Whether or not it actually ends up happening with this glass, who knows? But that's what GLS glass is. Right, enough talking about other people. How are we making it? How are we making it here? Well, we have gallium metal, and we can dissolve gallium metal into acids and form the gallium salt. And then I feel like, which is never a good thing to say in chemistry, I feel like we can bubble hydrogen sulfide through the gallium and it will precipitate out gallium sulfide. Maybe, it might do that. And we're going to do the same thing for the lanthanum. We already have the lanthanum salt, so all we got to do is bubble hydrogen sulfide through and hopefully get some of the sulfide out. Now, this might not work because the sulfides might be too reactive and it will react with the water that it's in and it might just get a big mess, but that's where I'm going to start because we can generate hydrogen sulfide with a method I sort of tried a couple of years ago now, which is sulfur and a candle. The bad part about that, which we're going to hit again, is that it really does kind of destroy the flask that it's in. Now, that video I did intend to clean that flask, but I think it's this one. Yeah, look, the flask is still dirty, like several years later, so maybe I'm just incredibly lazy. But anyway, we can generate some hydrosulfide, then we can make the metal sulfides out of the metal salts, and then we've got the sulfides, which we just need to melt together at a high temperature, but not like ridiculously high. We've had some videos recently where we've needed to go in excess of 1200 degrees, whereas I think for this, we probably only need to go to about 1100 degrees. So if we do that, we can melt the glass, pour it out, maybe anneal it if we can get it to a nice glassy state. So that's the steps. Dissolve up the gallium, make hydrosulfide, precipitate out the sulfides, melt the glass. Sounds simple enough? I mean, it doesn't sound simple in the goddamn slightest, but I think it's achievable. Okay, let's get to it. We have here our 2 starting materials, the Barracuda phosphate remover, 200 grams per litre rare earth salts, but we know from the MSDS that this is pretty much mostly lanthanum. I would say it's technical grade lanthanum, basically a waste stream from the mine that they've turned into a pool product, which is pretty great. And we have this unlabeled Ziploc bag of metal, which is not a great way to store a liquid metal. I got this metal, well over a decade ago now, and I made a video about it on the first Explosive Fire channel before it got deleted in I want to say 2014, and the video was terrible, but not like terrible in a fun way, terrible in like it was a bunch of kids with shoddy camera work and showing something not particularly interesting. But it got 300,000 views, I think, which was a lot for the time, seeing as I had 5,000 subscribers. But anyway, that's old YouTube from a little while ago. Anyway, that lump of metal from that video, I guess I just chucked in a Ziploc bag for another day, and that another day has arrived. Reasonably hot today, so we can see it's starting to melt a little bit. Don't quite know how much is in here, so 32 grams, 32.5 grams. That seems like a lot, especially for this method that we're not entirely certain is going to work, where we dissolve this in acid and then put hydrogen sulfide through that acidic gallium solution. Actually, it's not going to work at all if it's acidic. So it's got to be neutral, but then maybe we'll precipitate out the gallium oxide. Anyway, I have a lot of problems with this method. I'm not convinced it's going to work very well. So maybe we'll just get out maybe 10 grams or so of this, and we don't need to break up this metal. We can easily melt this metal. I'm just going to immerse this Ziploc bag in some hot water. and we should be able to syringe some out, which is a very cool property of dealing with this metal. Just melt the metal and move it around as you wish. Very cool. That looks good. Shiny bit of metal. Okay, maybe it doesn't react. I'll find another acid, I guess. Nothing really, maybe a couple of bubbles. Let's add a little more, a couple more mils. Watch this for me and let me know if anything happens, alright? I'll be back, alright? Yell out if anything happens. Take off. Just gonna move this outside. Quarantine. Humid. So the gallium has been reacting in this acid for the past, couple of days really. It kind of stops reacting pretty much altogether when I stop heating it. And it was a nice clear solution for most of it. But then right at the end here, I don't know, it's turned into milk. It should be dissolving. The solution's acidic. It's not like crashing out crystals, but I don't know. It just seems like a little bit of maybe hydroxide, I guess, refusing to redissolve back into the solution. So my patience has run out actually for it. It doesn't look like it's a heat that's out of solution, so I'm just going to filter it and then we can get to the hydrogen sulfide part. It'll be a nice clear solution ideally after filtering. While that's happening, let's go create our hydrogen sulfide generation system. All right, let's do that. We have here our 3 reagents for our hydrogen sulfide reaction: sulfur, some amorphous non-conductive carbon, and a candle. We're just using this as our paraffin source. People, very rightfully so, commented on the last video I used a candle that it's just very cheap to get big blocks of pure paraffin rather than using a candle. But first of all, I forgot to get nice paraffin for this, but also it's just funnier using a candle. It's fine. Okay, so we need 12 grams of candle, 6 grams of sulfur, and then I think last time I used about 8 grams of carbon, but it's probably a bit much, so maybe I'll cut that down to something like 6. I don't know, it's very vibe-based, this, but yeah, we're just going to be generating some hydrogen sulfide. I don't know why I'm working on the ground here. That's maybe because I don't respect these as real reagents, but let's set up an actual table and then I can put some actual glassware on there. It might make it look more like science. Almost immediately. Oh, come on. Wasting my time. What am I doing? Not near the chemicals. Move along, sir. Thank you. That's an acceptable distance, right? No closer. It is not completely done filtering, but it's been filtering for about 12 hours now. At least it looks good. Look, we got most of our gallium solution down through there. It's nice and clear, so we'll move on to the next step, which is setting up the whole damn hydrogen sulfide generation and seeing if it works to produce gallium sulfide, because we may have done all this and it's not going to work anyway, but we'll have some optimism. We'll go set up some goddamn poison gas generator. Let's go. Alrighty, I'm ready to call this a failure. There's a little bit of solid in the flask, but I think that's just because I was adjusting the pH with some sodium carbonate and I was trying to get it a bit more neutral. When you start putting it neutral, then the gallium starts precipitating out as gallium hydroxide, but if it's acidic, then gallium sulfide is going to react with the acid, so I just don't think this is going to work. And we generate a lot of hydrogen sulfide. You can see that's our bleach solution. The bleach oxidizes the hydrogen sulfide into sulfur, so that's why it's all yellow and chunky there. It's all yellow all through here, thanks to all the sulfur precipitating out, and got a little yellow tinge in there, which I think was a little promising because what we were trying to make is yellow, the sulfide, but I'm pretty sure it's just sulfur getting, you know, blown off out of here into there, which sucks. So that's a trash yellow. It's all trash yellow. I gotta clean all this. I was gonna try also with the lanthanum chloride here, but yeah, look, hey, if this doesn't work, then I'm not going to try again with this and not have it work. This is a mess. It stinks. It's been cooled down for a couple of hours now, actually, but there's still a lingering smell of, you know, it's kind of burnt tires and piss rather than just being like stinky farts from the hydrogen sulfide, because hydrogen sulfide is like the rotten egg fart smell, really. But when it's kind of pure like this and there's just so much sulfur, I think it's kind of a bit more acrid, a bit more kind of burnt rubber smell. It's not particularly pleasant. Yeah, it's actually extremely unpleasant. Let's put it that way. Damn. Anyway, so I'm gonna clean this up. This flask. Yeah. Fuck knows. But more importantly, what are we doing now? This is step 1. We don't have any gallium sulfide. How are we making gallium sulfide? I've got to think about that. Another synthesis of gallium sulfide. It comes from France in 2020, and it is a mechanosynthesis. So they took gallium metal, we got another lump here, and sulfur, grinded it together, and formed gallium sulfide. Simple enough, and we kind of have the tools to do it. I say kind of because they did use a plenary ball mill, which is like a high-speed, really good grinding ball mill, and it was also done under an inert atmosphere because this stuff is reactive to moisture in the air. So I'm not entirely certain we can do it with what we have here. We've got a rotary tumbler, which we used somewhat recently, but is somehow already covered in cobwebs, and we have a good... What's the material out of this? Ceramic. Oh, I've forgotten the exact material. But that's our ball mill, which we last used for the perovskites, which I still haven't cleaned. Look how fluorescent that is. That's crazy. Anyway, so that's still covered in lead perovskite, which somehow is still completely stable. Okay, that's very funny. But if we clean this off, then we should just be able to add some gallium and some sulfur in here and grind it. Hopefully, it stays dry enough to make some gallium sulfide. And this is the sludge from the gallium sulfide attempt before. I guess it went reasonably basic and precipitated out some stuff, but it's a bit sludgy now. It's verging on being a paste, but I'd still call it a sludge. I reckon we can recover the gallium metal from this. We'll come back to that. We'll put that to the side. I'm losing faith in my ability to do chemistry a little bit here, but we'll try this kind of bizarre mechanosynthesis. I don't know why I think it's bizarre. It's just always weird to think of doing chemistry by just taking two elements and grinding them together to make the thing. I guess maybe it's also bizarre because this is like going to be a liquid metal, but I guess when we're grinding it, we want it to be a solid. I don't know. I don't know why I'm overthinking this. Maybe I'm overthinking it. Maybe I'm underthinking it. Maybe I'm overthinking my underthinking. It's fine. We have to do step 1 is get this clean, because goddamn, we cannot grind in it now with that much lead contamination. So let's gently wash this with a little bit of acid, and that should destroy the perovskites, solubilize the lead, and then we can ditch it away and clean it off and store all the lead waste somewhere. Beautiful stuff. All right. That's step 1. Back in 10 minutes. Oh yeah. Oh, it's broken. Ah, ultrasonic cleaner. You're always the worst of the lot. God damn it. Exactly 10. Okay, so we have our clean and dry lead-free media here now, which is good. It's been in the desiccator, so it dries it off because we don't want any water reacting with our gallium sulfide as it's being formed. We have, oh sorry, ignore the vape here. It's a different project. We have 12 grams of gallium sitting as a nice little puddle of liquid there, and 9 grams of sulfur. The exact stoichiometric amount of sulfur to react with, all the atoms of gallium here is about 8.2, 8.3 grams. So 9 grams is about a 10% excess. They do this in the paper. Mostly they do, just the stoichiometric amounts. But here I want to use an excess of sulfur just to try and stop the gallium reacting so much with the air when it's, ground up into little particles and making so much gallium oxide, and also just making sure that there's definitely enough sulfur, because if we don't have enough sulfur and we've got too much gallium, then the sulfide we make is going to be all weird. But excess sulfur shouldn't really affect it at all. In fact, we're just going to be heating this up later when we're making the actual glass, and the sulfur will just boil off at that point. So I don't mind having excess sulfur. In the paper, when they use a 9% excess, they get different crystal structures of the material that forms, or like the ratio of the crystal structure. There's a beta form and a gamma form. It's just the spacings and the arrangement of the lattice in the gallium sulfide. Once again, this doesn't matter because we're heating it, and when they heat it above 450 degrees, it all resets into this alpha phase anyway. So we don't really mind about this polymorph stuff. So that's what we have here. We need to just grind this up. But again, I really want to protect this from moisture. It's so absurd saying this. Previously, I was trying a synthesis involving water. Of course, it was not going to work. Anyway, I'm not going to get hung up on that. So we're going to run it in this bad boy, the tumbler, but we also kind of want to protect it from air, I guess moisture and air really. French paper does this under nitrogen, and I assume they have probably a nicer setup than this. I was wondering if I could run this, with the ball mill inside of this chamber. Like, I'm not going to be able to seal it, but it's probably fine for me to just mostly seal it and then just flow argon in, and then the argon will keep flowing out and it'll keep a lot of the air out. I don't know. It might help at least protect the gallium sulfide a little bit. It's probably going to look ridiculous though. So oh. Like if I rotate the world 45 degrees, then it's flat. Is that too ridiculous? I've built worse. I know that's not saying a lot, but so ridiculous. This video has been such a mess. That's so funny. We're doing this. We're absolutely doing this. Alright, I'll just put the sulfur in first. Just crush that down a little. It's in very large pieces. Getting there. Alright, it's gallium time, let's do it. Alright, argon on. Alright. Go. Oh, it's only been a couple of minutes. Only been like 4 minutes of grinding. There's some green. It's looking kind of green. Like it's greenish. This might be inadvisable, but I'm going to try and run it without the lid, because I'm interested in what's going on. I got the argon flowing. Hopefully the powder doesn't fly everywhere. Let's see if it does. Okay, here we are. Oh, I can turn the argon off as well. Oh man, that's a lot of argon too. I used about a third of the other cylinder, the last third, and maybe 2/3 of this, so probably about $100 worth of argon I've used for this. I really should have sealed it. I haven't looked at this for a little while. It's had probably 3 hours of grinding, maybe a bit longer, but an hour or so was last week, and I stored it in a desiccator, and I've done a couple hours today, but I haven't really looked at it the last 2 hours or so. It's been, roughly sealed because it's absolutely pouring with rain, and we're making a moisture sensitive compound. And last time we looked at it was black, which I think is really gallium sulfide. The French paper that we're following was very kind enough to actually give images of what we're expecting the material to look like. And so it obviously starts off with this metallic gallium and yellow sulfur, but theirs goes to this black gallium sulfide very quickly because they're obviously using a much more optimized grinding system than whatever the hell this is. At least I think so. I don't know. I'm losing touch with the ball mill community, you know? What am I saying? So it's this black gallium sulfide, and then it goes, unfortunately, it goes more yellow, and that's what they're actually looking for. So we are actually hoping it's kind of gone a little yellow rather than pitch black, because we want this gallium 3 sulfide, so Ga2S3. That's what we need for the glass, rather than just gallium 2 sulfide, which is gas. So I did heat it up at some point. If it was above 35 degrees or so, then any little bits of gallium would melt, and I think they're going to react a lot faster as they get ground down. Because when we looked at it about an hour in, you could tell it was black, but it had little flecks of solid gallium metal in there still. So I did have to heat it to get it going, but it's still quite warm, so I expected any gallium would still be liquid. Not that there should be any gallium left anymore, it should all be gallium sulfide, hopefully. But it's warm just from the grinding, but also from this motor. Alright, I'm nervous, you know. If it's still black and still looks like it did after an hour, maybe I just gotta add a little bit more sulfur and then just keep grinding it, but I don't want to keep grinding forever, you know. I gotta retire at some point. Have I built the suspense for the reveal up enough? Because sometimes we get incredibly disappointed with this. Oh, so the bit where I said there shouldn't be any gallium, there's definitely silvery liquid metal in there, right? Did I measure my ratios wrong? Ooh, this feels extremely compacted. Maybe that's why. I should be getting it out and stirring it. Okay, well, I guess I will have to do what I said, which I don't really want to do, but I suppose I have to do what I say sometimes, which is just add a little bit more sulfur and get this grinding again, because I guess there's just too much gallium. Got to stir this all up too. It's not really a very optimized grinding setup, which is saying a lot. But the fact that we're making a moisture sensitive compound and it's very close to working, it seems, while it's raining in my shed here is good, Okay, let's go find the sulfur. I'm gonna add a full gram more. We'll add an excess, burn off any excess anyway when we're heating it. Just wanna see if it changes from this black. Okay, I'm done with this. I'm so done with this. This has had many hours of grinding. Whoop! Many hours of grinding across multiple days, across multiple weeks. I'm sick of this. What we were waiting for is this black powder, which is, I guess, a mixture of gallium 2 sulfide and gallium 3 sulfide, so the GAS and the Ga2S3. And we wanted to see that lighten in color to kind of indicate that we're going to a more pure Ga2S3, which is the compound we want, the stuff we need for the glass. And it really hasn't lightened in color at all. In fact, what it's really doing is sort of just like coating all the media in a way that I can't seem to clean off very well, or kind of knock off to allow it to keep grinding. My solution was just to add more sulfur because okay, I shouldn't. It's getting to the point where we shouldn't do this inside, which is a great sign, but there is a hydrogen sulfide smell. Yes, increasing the sulfur in this reaction mix should hopefully drive it towards this Ga2S3 because there's kind of like more sulfur per gallium. And so I added an extra gram of sulfur and then like another gram of sulfur, and then ended up adding in total another 12 grams of sulfur, which is a huge amount. This mixture has heaps of excess sulfur, which doesn't look like, because once again, it's still incredibly black. This is mostly bright yellow sulfur, and it looks looks like this. So I'm going to heat this. I'm going to heat this to 350 degrees to try and drive off that excess sulfur, basically boil it off, and then hopefully maybe the stuff we're left with is at least reasonably pure gallium-3 sulfide. And do I have any reason to believe that that would be the case? No, not really, but this is all the time I can spend on the grind without going insane. The grind life is not for me. So I'm gonna get out some of this black powder, put it in here, and then heat it to 350 degrees. Hopefully it doesn't reek too much. I mean, a great sign is that this does smell very bad, and it does react very lightly with water to form hydrogen sulfide, which is this horrible smell. It's a very toxic gas, very detectable in small amounts. So great that it can produce this toxic gas. It means it's the compound we kind of want. But the fact that it doesn't kind of completely react means that there's only some of the compound we want, and a lot of it is the compound we don't want, and I guess excess sulfur. So like, we've made the thing that we want, but it's just not at a good purity level. I mean, it could only be a couple % of this overall black material, and that's just not going to be good enough for the glass forming. So that's a reality, but I just can't keep this grinding forever. Like, I'm going to go insane. This project has actually been going on for months. So let's get this heated to 350 degrees and just see what it looks like. Maybe once everything boils off, we're left with something that maybe resembles the thing that we actually want. So a little bit of optimism here, which nothing has gone our way this video, but let's give it a shot. Let's give it a shot. Ooh. That's one way to boil off the sulfur, I suppose. Whoops. Here we are, we end up with a vaguely strange, metallic, alien-looking material. I mean, it's certainly not gallium metal, it's certainly not sulfur, it's definitely not gallium oxide, so, you know, it's definitely a gallium sulfide of some sort. Whether or not it's enough of the correct gallium sulfide for our glass is yet to be seen, but this is as good as I'm gonna get it, I think. I'm definitely gonna carry that forward. Wow, that was a bit intense. I mean, I'm pretty bad at predicting the timelines for things to happen in this project. I mean, that's exactly what I wanted, the sulfur to kind of boil off, but I thought it might take maybe half an hour, but it really happened in about 2 minutes. In fact, it basically all boiled off in about 10 seconds there at 350 degrees, which in hindsight is actually not that surprising. And did burst into flames there, which wasn't great. And we've sort of yellowed my furnace, but hopefully that all cooks off. I'm glad it wasn't any larger scale, otherwise that would have gotten a little bit more hairy. Look, hey, it's what we wanted. The grinding took an extra 4 weeks, but the sulfur boiling off happened pretty much instantly. So, you know, that's a time save, I guess. Look, hey, we've made the gallium sulfide, the G of the GLS, and I guess half of the S. But we got to turn ourselves towards the L, the lanthanum. How do we make this lanthanum sulfide? So we've talked about previously the fact that you can buy lanthanum from the hardware store in this phosphate remover, which is like a soluble lanthanum chloride. But given the fact that how long we've spent, how difficult it's been getting the gallium sulfide, lanthanum sulfide I think is more reactive, so it's going to be harder to make. So I'm going to go see if I can buy some. Look what we have, packaged straight from Poland. Lanthanum sulfide. So this is the one we want. They also sold this one. I just thought I'd get them both, just in the off chance I was wrong about which one we needed. This is only 3 grams, but it should be enough to make at least a bit of glass with it. That's very exciting. And while I was there, I also got big lump of lanthanum metal in there. I don't know really what I'm going to do with it, but thought it's a lanthanum video, you know, I might as well buy it. Actually, whenever I film the intro, I said something like, oh, lanthanum has no value, you can barely even give it away. And it's funny because then I paid for 100 grams of this, and then the guy at Onyx messaged me and he was like, oh, I've given you like 130, 140 grams. It literally just gives away more. He's like, well, I don't want this shit. It was pretty cheap, and he was still like, nah, I'll throw in some extra, like, no one wants this. And I think that's, well, actually, no, it's not quite it. There should be one more. Yeah, I don't know, it's just a bar of palladium. The palladium prices like plummeted recently, so it's now back to normal levels. I don't know, I don't really follow the thing. So lanthanum sulfide synthesis complete. We did it. God, chemistry's easy, isn't it? Chemistry's easy. Let's make some damn glass. Let's finally make some damn glass. Here we are. It's glass time. So we have here lanthanum sulfide that we've bought, just a bit less than 1.5 grams, or about 1.5 grams. I've already forgotten the number. And then our gallium sulfide here. And I know what you're thinking. This looks exactly like what we wanted it to. So did I cheat? Did I buy some new stuff? No. I've been keeping that weird metallic stuff that we made the other day, or like metallic-y looking stuff. And when I ground it up into this powder, it looks exactly like what we want. So the optimism is absolutely flowing through me today. I couldn't believe that when it like ground up to this nice yellowy green powder. It's still reactive to moisture in the air, so I can't spend too long yapping. We've got a ratio here of 70% gallium sulfide, 30% lanthanum sulfide by molar weight. So, 70% of the atoms are gallium, 30% are lanthanum, and that seems to be the standard for this glass, this 70-30. There is a glass forming range, which varies with the different in composition. So outside of that range, it doesn't form a glass, which is kind of, I guess, a little bit weird to think about, but the glass is really more of like a frozen liquid, and the atoms kind of get confused and don't crystallize. So you've got gallium sulfide and you've got lanthanum sulfide, but you don't have crystals of lanthanum sulfide mixed with crystals of gallium sulfide. You just have a mess of all the atoms. None of them form crystal structures. They're just kind of like mixed perfectly and frozen. So that's what we want. We want to form this nice glass. So we obviously have to heat it, melt it together, and then it'll melt, and then we'll cool it down. Potentially reasonably rapidly, we'll cool it down to kind of set the glass and not let it crystallize out. We're going to preheat it here at 400. Sure, why not 400? The papers we're following does a 350 degree preheat. It's fine. I think our stuff's a little bit more impure, so 400, sure. That's my problem. I have to change something. Always have to change something. So we're just going to load it into here. This is a pretty standard alumina crucible. Hopefully it all fits. And we're going to leave the lid off for here because we want to just drive off any last volatile stuff, like any leftover sulfur. We're still looking a little yellow from the other day. And then we need to heat it up to about 1,100. This technically goes up that high. I think 1,150. All the damage from it was me setting it to its maximum temperature, and then all the paint starts peeling off. So it's not particularly nice for this furnace to go up to its maximum temperature, and the stuff we're making is still reasonably reactive, so the longer we have it heating, kind of the worse it is. So instead, we're going to use the equally dirty, or in fact, potentially even more dirty, fan favorite microwave, and the microwave furnace. So this is a little thing off eBay, which I've used a couple of times now. It's just this little ceramic crucible with, I think it's silicon carbide, but this really, really strongly absorbs the microwaves, so it gets super hot in here very, very quickly. So put our crucible, after it's preheated, get it out, 400 degrees, we'll put it in here, put it in the microwave, should get to 1,100 degrees reasonably quickly, like within 10 minutes or so, 10 minutes of microwave cooking, and then hopefully it doesn't all spontaneously decompose into sulfur and hydrogen sulfide and burst into flames, but equally so, I hope it doesn't just stay as raw powders. I hope it does melt and we can see a glass. Just want to see the glass form. All right. I've needed positive vibes for the entire project for this, but this is where I need the most positive vibes because there's a chance this genuinely works. Despite everything going completely wrong for this entire project, over the next hour, we could see results, and that's crazy to me. I forgot I scorched it last time I used this. I hope it still turns on. I should check that. Anyway, well, let's mix and just hand grind these two powders together before loading in the crucible. And let's get it damn cooking. All right, positive vibes. Thank you. Deserve that. Good. Pretty hot. The other one's pretty hot. Oh yeah, great. Everything's fine. Okay. It's melted. It looks melted. What? perfectly. Alright, we're going to attempt to pour. It's liquid. It's definitely liquid. Holy dooly. Oh, it's so close. Come on. Gotta drop now. Oh, it's so dark. It's so dark. Okay, it's the dead of night now. I'm nearly at a loss for words, which is saying a lot for me. This looks exactly like it does in the papers. It's orange glass, transparent. It's exactly what we want. I thought at most we would maybe get something that sort of resembles a glass, but the fact that it's worked this well, we managed to actually pour some out. Of course, very limited by my sort of glass handling skills and pouring, but I didn't feel like I could hold a blowtorch to this glass because it's still a sulfide glass. I mean, it's oxygen free. Kind of weird to think about. Tick for the microwave furnace again. That's incredible. Thank you for your positive energy. I hope it comes across how unlikely that was to come together. That's amazing. All right, well, thank you very much. I'll see you next time.